All right, good afternoon, Count Two people. So if you're watching this kind of contemporaneously, C&M had a flood last night, and that is possibly, if some of you were working on your homework, why you were unceremoniously dumped. So they're working on that. I did not get a message saying that it is fixed, although I can get into everything I needed to get into so far. So I suspect that they have the situation under control. So if you were wondering, that's what happened. Okay. So today, what we're going to work on here, right, is we're going to have something called an improper integral today. Okay? So I don't really have too much of a care as to how they actually classify them, but your book does tend to run into that. And I will note some differences as we go through. Okay, so today we're going to do improper integrals. Okay, I do have, we are going to talk about approximations of integrals in a little bit, so we are going to have numerical integration, but I thought we would go with the improper integrals first because it's sticking around with some of the stuff that we can do, and yeah. So in improper integrals, we have two types. Okay, we have type 1, which I believe is when we have an integral from, say, 0 to infinity of e to the negative x dx, all right? And it is our job to figure out if this converges or diverges. Okay. Now, I want to be real careful because in calculus, when we say it diverges, it doesn't necessarily mean it goes to infinity. It just means we can't put a number on what's going on here, okay? So if you remember back from Calc 1, right, if we did the limit, say, of x goes to infinity of sine x. Now, we're not taking a derivative, we're not taking an integral, we're just looking at the integral, we're just looking at the limit as x goes to infinity of sine x. And you say, well, what the heck does sine x look like, right? Off to infinity, and it just kind of looks something like this, right? And it doesn't necessarily get any smaller, right? It stays between 1 and -1. But if I ask you, like, what's happening here, and it diverges, right? We don't have an answer for this because it keeps wiggling back and forth. Okay, we're not trying to figure out the integral, right? Even if we were, right, we get some positive amount, we get a negative amount, we get a positive amount, we get a negative amount. I mean, there's no way to really tell what's going on here. So even if we had like an integral sine x from 0 to infinity, okay, we couldn't really say too much about this because it's, the area under the curve is going to be constantly changing, positive to negative, right? And if I take the whole thing here, right, we get an area of 0. Oh, but then we get an area that's positive, and then we get an area that's still positive, but then it's negative. So when I say diverges, right, this is not going to infinity, right? It's pretty much staying between some small positive amount, and we have a negative amount, and it'll end up being 0 at the end of each cycle. So it certainly isn't getting any bigger. Okay, so when we say diverges, all we mean is we can't put a number on this. We have no idea. Okay, so I just really want to make sure that when you say that something is divergent, it doesn't necessarily mean it goes up and away forever. It just means, well, we can't analyze it. Okay, so yeah, that's our type 1, and that's when we have an infinity somewhere in the integral. Okay, so another type 1 would be like negative infinity to positive infinity of e to the negative x squared. Okay, so that's still type 1 because there's an infinity here. Okay, that's what they're going on about when they're calling it type 1. Now, type 2, and these, I always found these to be like, these are more problematic. Okay, because sometimes they're sneaky and they're hidden and you don't know. Okay, so if I want to do something like a 1 over an x minus 1, and I want to integrate this between 0 and 3, well, there's a problem when x equals 1, right? So if I'm going to be doing this, there's a spot, right, when x equals 1, which is right in the middle of my integral, where I'm going to be hitting a singularity, right? I'm going to be hitting some kind of a vertical asymptote. Like, what gives? What am I supposed to do with that? So you have to be really careful with these because, I mean, to be fair, your book mostly puts these kinds of things. You know, they'll do something like this, okay, and you don't try to hide it and you don't try to be sneaky. But not every book is written the way your book is. Okay, and for some good and for some bad. I mean, sometimes your book takes the harder path and does the harder thing. Sometimes it doesn't. And most of the ones I've seen these days, they tend to do a type 2 integral. So it's the endpoint is the one that's problematic. Okay, but just because you're used to saying that, you have to be, you have to be careful when you're integrating, because if you end up integrating some function like this over something that you shouldn't, you're going to get an answer, but it's not going to be the right answer. Okay, because you have to be real careful when you're integrating over a discontinuity. So that being said, that's why you might look at that and you say, wait a minute, this is chapter 2 stuff. Why do I have 2 sections in chapter 2 in the middle of my integration problem? The integral of in the middle of my Calc 2 problems. Right? And the reason why is because we want to remind you about limits and continuity and what we can do about that. See, if I have if I have a f of x, so we'll do an easy one. It's 3 from x is 0 to x is 3, and then 1 from x is 3. Oops, not one of those. Strictly greater than to say x is 4. Okay, and I don't really need the. If I didn't write down this thing, let's go ahead and take both of these out. Can't force a habit to write that. Well, what's that graph look like? So we go from here up to here. Oops, no, there's a dot there. And then from here to 4, there's a dot there. And the reason why I made this, the kind of graph it is I'm going to ask you, like, can you figure out the area under these 2 curves or under this curve here? Like, sure you can. It's box 1 plus the area of box 2. We're done. So you can integrate over, right, over a jump discontinuity like this. But if I asked you to integrate, say, 1 over x squared from -1 to +1, right? We got something like that going on, and maybe not anymore. Okay, so maybe this, you're looking at this like, I don't think I could, not until I'm finished this section, I'm not going to be able to integrate this. All right, so if it's jump discontinuity, there's often times we can integrate it. Okay, I'm going to say if there's maybe a listable number of jump discontinuities, maybe finite would be better, because then you can actually do it. I would not, if I gave you the function x is an element of the irrationals, x is an element of the rationals, I would not want to integrate this, okay, because it looks awful. All right. So what's going on here is that I think our integral is going to be 0, but you'll need a lot more math to do that. Okay, but what that graph looks like, right? Well, when x is in irrational power, it's 1. So there's a whole bunch of dots here. And when x is a member of the rational, well, there's a whole bunch of dots down there. So all you've got is a collection of dust up here and a collection of dust down here, and you're trying to integrate those, and there's really nothing there. Okay, but this is not right. This is not a good choice as a math problem for us right now, because we won't, in this class, we will not have the tools to do this. Okay, but all they are is jump discontinuities, right? So it should be okay. Nah, not really. But if I ask you a bunch of squares or rectangles, right, or we have like you get a parabola here, and then you got a parabola down here, and I ask you to integrate that, well then sure, we can just break that, integrate this piece, break this. We have an area 1 here, we have an area 2, and everybody's happy. Okay. If you list your Calc 1 friend to integrate this, they're not happy because I snuck in 2 problems where they thought they were only going to have 1. But it's not the worst thing in the world. Okay. So that's why the beginning parts are there, is because we want you to remember, like, hey, what's a discontinuity look like and how are they classified? So we have this type, and then we have jump test discontinuities. I don't think anybody ever showed this or tormented you with this kind of thing before. That's fine. They shouldn't. I shouldn't have. Okay. But then we also have discontinuities like this, or discontinuities like 1 over x, right? And how are we supposed to integrate stuff like that? Okay, so that's why you're going to see that beginning stuff. And the other reason is, we're going to have to evaluate limits, because if I'm going to do something like this, I'm going to have, like, say, from 0 to infinity of x e to the negative x dx. We'll probably start with this one. Well, the first thing we're going to have to do is, okay, so I'm going to apologize in advance, because when we teach this face-to-face, we demand that you are better at your notation. Okay, so we don't want an infinity up here in the integral sign. Okay, now when you get to physics, they're going to abuse this all the time. Okay, they're just going to write this and not care. However, this is the class where you have to tell me that you know how to translate this exactly, and you're going to have to write this thing down. All right, so it's kind of like this drives me nuts, by the way. What's the difference between less and fewer? Right? Fewer refers to a countable collection of items. Less refers to a measurable. Right? So you could have less time, but it would be more appropriate. It would be appropriate to say, like, you don't have less seconds, you have fewer seconds. You can have less time, but fewer seconds. Less time, fewer minutes. Okay, I know they effectively say the same thing, but you're counting the seconds versus measuring the time. So when people say, "Oh, there's less voters," I'm like, "Oh, please don't do that. There's fewer voters. We count them." Okay, so drives me nuts, but and there it is. Okay, but this is the class where you have, we're going to get on you for using one or the other. Okay. One of the other things, I don't know if you've ever taken a statistics class, especially a 100 statistics class, level 1, and you have to calculate a sample standard deviation. In our statistics classes, a sample standard deviation has the symbol S. A population standard deviation has the symbol Greek S. Okay, that's my sigma. When you leave 100 level statistics, you are going to find that people write sigma every time they use a standard deviation, even though almost always they're referring to a sample standard deviation, but they still use this symbol. I don't know why, maybe because it looks cool, whatever, but that's not something that is in freshman stats. We make a huge deal about the fact that we use this symbol or this symbol depending on the context. And then once you leave, it's okay. You can use whatever you want. Okay, your stats teacher might get mad at you someday and do that, but so be it. I've been, we've been around the block. We've been in the world. Everybody uses sigma for any standard deviation they mean, and it's just up to you to figure out what the heck they're talking about. So this is the class. You're going to have to write this thing out properly, and the way you do that, right? Pick your favorite letter. I think your book chooses T. So we're going to say we're going to change this to the limit as T approaches infinity. integral 0 to t of x e to the negative x dx. Okay, just don't pick x. That'll make things confusing. Pick any other letter. Okay, and that's what we're going to have to figure out. Now, I know it's been a while since, I know you're taking your tests in integration techniques now, but usually once we're done with that for a little bit, you forget some things and you remember that this is an integration by parts problem. So now that we've changed this to a t, now it's safe. We're just going to go ahead and integrate. So we're going to say let u equal x, du equals dx, dv equals e to the negative x, and v is equal to negative e to the negative x. Okay, and what are we going to do here? We're going to say, well, this is negative x e to the negative x minus integral from 0 to t. We still have this limit out here, right? Limit as t goes to infinity. And technically, right, there's going to be a bar here, 0 to t, because we've evaluated this part of it. I usually wait till the very end to write this thing in, but yeah, here we are. And we have e to the negative x. Okay, so this is equal to limit. Yes, you have to write this. All right, and this is going to be negative x e to the negative x plus integral from 0 to t e to the negative x, which eventually is going to be limit as t goes to infinity, negative x e to the negative x minus e to the negative x, and we are evaluating between 0 and t. Okay. One thing we could do, we take out the negative signs and we could say this is limit as t goes to infinity of e of x e to the negative x plus e to the negative x, and we've got t to 0. Okay, so what I did is I just changed both of these signs to, I changed both of the signs and then swap the limit of integration, swap the orders. You're allowed to do that. Okay, let's go ahead. Let's evaluate at, all right, this is x equals 0. All right, so we have 0 times e to the 0, negative, plus e to the negative 0. What is e to the 0? Can we do that? E to the 0 is 1. So if that's 1, it's 1. 1 times 0 is 0, and 1 is 1. Okay. Minus, and now we have our limit, right? As t goes to infinity, right? And we have t e to the negative t plus e to the negative t. Okay. Now here's we have to remember, like, well, I've got t going to infinity, but I've got e to the negative t going on here, right? And t is again going to infinity. So who wins, right? Is this going to be infinity or is it going to be 0? What's going on? Well, there's a number of ways you could do this. And even though this is taken out like a cannon to kill an ant, all right, we're going to go ahead and set this thing up as as L'Hopital's problem. So why are you doing that? Because other than remembering how to spell or pronounce L'Hopital's, have you practiced recently? No, we probably need to. So derivative of t with respect to t is 1. Derivative of e to the t with respect to t, e to the t. So if I'm looking at my limit as t goes to infinity here, 1 is unaffected by this limit, so that's going to be 1. T goes to infinity of e to the t is infinite, and that goes to 0. Okay, there's a number of other ways of doing this problem. All right, so you didn't have to use L'Hopital's on this one, but I chose to, just because there are going to be times when we may have to use L'Hopital's to evaluate a limit, and I want to remind you, like, that is a tool that you have. Okay? E to the negative x, right? E to the negative t as t goes to infinity. This is also, right, it's 1 over e to the t, it's also 0. All right, so this is going to be 0 and 0. Okay, so we have 1, right? It's 1 minus, and both of these limits happen to be 0. My answer here, right? So this converges, right? Because we got a number, so it converges. And it converges to 1. Okay, so that's what we're doing with that. Okay, so let's see. When we get to probability, that'll be nice because there's a reason why I picked this problem first, is because this is a very typical kind of probability problem. It's called a, well, what's this one? It's not, it's a gamma function. So a gamma distribution is what this one is. So, yeah. Something like that. Okay. And getting the probabilities is between any two values. Okay, so it's a nice, it's a nice intro to well, not intro, but it's a nice, like, after you've had calculus probability problem, because you have to do integration by parts, and then you have to evaluate different pieces of it, and then go on from there. Okay. So, nice problem. Okay, I'm partial to this one. All right, so let's see what else we're going to do. Oh, and this was again a type 1. Okay, well, what about something that's what about something that's a little bit different here? Let's see if we can find a good one here. Let's see. This is all the okay, divergent or convergent type of things going on here. Okay. Let's see if we can. This is no. I want to do a. I want to do a problem. There we go. Yeah. So they don't have you integrate. They don't have you evaluate this one. They just say, well, what's going on here, right? And they have a 2. Hey, wait a minute, what's going on with that? If I put 2 in, I'm not going to do so well. Okay. So again, why don't we go ahead and see if we can do this one? So we're going to integrate between 2 and 3. Okay. And we are going to say this is 1 over, right, x minus 2 dx, yeah? That's the problem that we have. All right. Oh, x over x minus 2. Better. Okay. Okay. So the first thing you notice is like, wait a minute, if I put 2 in here, I'm going to be in trouble. So pick your favorite letter. How about we limit as a goes to 2? And we have a to 3 of x over x minus 2 dx. You remember how to solve these. Okay. So what we could do is we could set u is equal to x minus 2. And then du was dx. Great. That is going to be so useful because we're still stuck with this thing. Okay. So what we're going to do here is we're going to say u plus 2 is equal to x. All right. So what we have here is we have limit as a goes to 2 from a to 3. Okay. And then we have a u plus 2 over u. And then we have a vu. Okay. And that is equal to a3. What the heck is a? I know it's a lot of writing. I apologize in advance for that. I know it's a lot of writing. But this was 1 plus 2 over u. Okay. du. So the first one's not so bad, right? I don't like doing that. Put u there for u of a, u of b, kind of thing. Okay. So we could change the limits. All right, so this is going to be u plus 2 ln u. And we still have a limit, right, as u of a goes to 2. And we have a and 2 here. So let's go back to x's, so that'll be nice, a little bit easier for us. So we have the values, right? We have limit as a goes to 2. We have x, what was it, x minus 2, x minus 2, plus 2 ln, absolute values rather, and x minus 2. Right? And we are evaluating from a to 3. Just to draw this out a little bit, we can evaluate it at 3, right? So this is x equals 3, and we're going to say, well, this is 3 minus 2 plus 2 ln 3 minus 2. It's going to be natural log of 1, right? It's a natural log of 1. Remember that offhand? Natural log of 1 is 0. Minus, and then we have the limit, right? We have the limit as a goes to 2, and then we have, right, a minus 2 plus 2 ln a minus 2. Well, that's not a big deal. We just plug the limit in, right? Direct substitution. Easy. Oh, what is the natural log of 0? Right? So remember what the natural log looks like. The natural log looks like this thing. Right? Log of, natural log of x minus 2, rather. It's going to be a horizontal shift over 2. So we're going to be looking at something like this. This is 3. Okay. So what's happening when we get to this limit here? Well, this is going to go down to negative infinity. I can't add numbers to that. That ain't going to work, right? I mean, I can try it, but it's not really going to do anything. So at this point, we get divergence, right? When we try to evaluate this limit, we get a negative infinity. That's not a number. It's a concept. Diverges. Okay. So this integral diverges. Okay. Now, is there any other, I mean, you have to think about, like, how or am I supposed to evaluate this? Okay. And if you only have one limit that you're dealing with here, then chances are you could probably just, use a graph, use any of the other tools that you've learned about limits from Calc 1, which is why you did the previous 2 homeworks. And it's going to be okay. When you have competing limits, right? If I have a natural log over a natural log, then we got to use things like a L'Hopital's, right? Or we have a few other ways of evaluating limits like that to see what's going on, but you have to check those out. Okay. Let's see. I kind of want to call today a little bit short for us. So I think that's what I'm going to do before we get into too much trouble. See, this one's, oh yeah, cotangent of 0 is not so good. Okay, so that's the kind of thing that we're looking at here. Again, they didn't ask us to do this. They didn't ask us to evaluate them. In this case, part A, infinite discontinuity, type 2. Okay, so I may have got my type 1 and type 2 mixed up. Fortunately, it is never a question I'm going to ask you. Okay, so we're going to be okay there. All right. So yeah, that's what's going to happen with that. So yeah, I'm going to stop us there. We will come back and we'll do a little bit more tomorrow. Right? But important to know, like important to be able to evaluate the limits. Again, this is almost all about the technique of writing it down. Okay, so when you have a limit from an A to a B, and B is going to be some kind of wonky thing, you're going to pick a favorite letter, limit of B goes to B, and then you're going to do your A and big B of whatever function you have to deal with. Okay. And then, unfortunately, what the heck was his name? The first ghost that Scrooge met in Christmas Carol. I think it was Marley, something like that. He had to drag around his chains with his wealth all throughout the afterlife. These are your chains. Okay, you're going to drag them all throughout the entire problem. So this gives you some kind of poetic idea of dragging this limit around, and that's just what we have to do with it. So my apologies. I had to do it too. It's a rite of passage. So anytime somebody else says to you, hey, I took Calc 2, like, hey, remember improper integrals? I'm like, oh, I hated those. It's the same thing. Everybody's got that same story to tell. So it's my pleasure to make you have the experience as well. Okay, we'll do a little bit more with this tomorrow and work that. Okay, so thank you for coming, and you guys have a great day, and let me know if you have some problems.